everyone and welcome to Magnetic Circuits course, video number 4, Inductance Design and Calculation. Let's start. What we covered so far. In video number 1, after the introduction to this course, we introduced the sources of magnetic field. In video number 2, we looked for what is a magnetic circuit including the pH curve. In video number 3, we had the analogy between magnetic circuit and the electric circuit. I'm going to add in the comments the links for these videos. Now we are going to start for our topic. To find an expression for the inductance, we need to start from Faraday's law. When Faraday was sitting in his lab, he applied this circuit, applying a DC source to a coil like this one. He noticed that the ammeter read nothing. Once he opened the switch, he noticed that the ammeter makes a deflection. So close the switch again and open that one again, find that the ammeter can make some deflections. So in this case, he swapped the source by AC source or a source function of time. Hence, he found that in the other side that there will be a reading for this voltmeter. So there will be induced voltage. And we have the well-known equation for Faraday's law that induced EMF in any closed circuit is equal to the time rate of change of the magnetic flux linkage by the circuit. E equals minus N d phi by dt. And N d phi equals d lambda, which is the flux linkage. We know that one from the previous video. So the negative sign here is Lenz's law, where the induced voltage acts in such a way to oppose the flux producing it. So we are going to consider that one if we are going to use dot convention or the direction of the current. So we can write the equation using Kirchhoff voltage law that V of t equals I of t multiplied by R plus E, which is the induced voltage here, equals N d phi by dt or d lambda by dt. So the equation, that one will be like this way. V of t equals I of t R plus d lambda by dt. But that one is a coil, so we can write that one as V of t equals I of t R plus L di by dt. So if we equate this part by this part, so this means d lambda equals L di. And if we integrate, so this means lambda, the flux linkage, equals Li, or we can write that L equals lambda over I, which is the flux linkage over the current. What we can conclude now that the electric behavior of the magnetic component can be represented by inductance L in series with resistance R. R could be the internal resistance of this coil. So how to calculate the inductance for a coil like that one? So there is a coil with number of turns N wound in an iron core, and there is a current I injected to this coil. So how to calculate the inductance? So we know that lambda equals N phi equals Li now. So N is the number of turns, phi is the flux in Weber, I is the coil current, lambda is the flux linkage in Weber as well, L is the self-inductance of the coil in Henry. So we are going to start from the first equation, that's L equals N phi over I, but we know that phi equals BA. B is the flux density, A is the perpendicular area. So A here, something like that one. That one is the phi. So phi applied to this area will give us B. But we know that B equals mu H, which is a magnetization curve for this iron core. So if we have a specific mu node mu R, so we can write this equation as B equals mu H. So N mu H A over I. What is the relation between I and H? We know that Ni equals HL. So we can write I equals HL over N. So that one is HL over N. We're going to cancel H with H. So that one will be N square over L over mu area. And we know that one before. That's reluctance equals L over mu area. So the inductance will be N square over reluctance. So we can calculate or design the inductance based on the number of turns and the dimension of the core and the material of the core. So if we have a certain magnetic length path, certain area, and certain iron material, we can have a specific reluctance. And when we are going to wound that one by a certain number of turns, we can design this inductance. For example, if you like to have 200 turns, so 200 square over a certain reluctance can give you, for example, 1 millihenry, 2 millihenry. So how you are going to find the reluctance? Reluctance is L over mu area. So you are going to design the core with a certain iron material. So you know mu node and mu R. So what will be L and A, which will give you this inductance. So we call that one design equation. Now we know how to calculate the inductance, N square over reluctance. So the question now, to have a certain number of turns N, how to wind this coil around the core? So to answer that one, we need to ask ourselves another question. Winding a coil on the core, smart or risky? So if we have a magnetic circuit like this one, 2C cores, and we try to wind that one, as we can see here, is that a good practice or bad practice? That one is bad, because you have a direct contact between the coil and the core. Not a good practice to have direct core winding. Why? Number one, electrical insulation. The iron core is a conductive material, and if there is any damage to the wire insulation, it results in a short circuit or interturn short circuit. That one is going to increase the leakage path. Number two, mechanical protection. Winding directly on metal or sharp edges can scratch or destroy the wire insulation. That one takes us back to number one. Number three, eddy currents. Direct contact can increase the unwanted eddy currents, especially with AC excitation. Number four, winding quality. Direct contact leads to uneven spacing, messy winding, and poor stability. Look here for the one we did. At that time, we are not going to have a concentrated coil. So in conclusion, direct contact is not ideal and not recommended for most designs. What we should do? So what is the best practice for coil winding? We are going to use coil former, or we call it bobbin. So what coil former looks like? Something like that one or that one. So a bobbin or a coil former is a non-conductive frame, usually plastic, that the coil is wound onto before placing it on the magnetic core. So what are the advantages of this coil former compared to the direct contact? So advantages of coil former are: number one, electrical insulation. Provides a barrier between the wire and the core and prevents short circuits, and definitely reduce the leakage. Mechanical protection. Protects wire insulation from sharp edges of the core and reduces risk of damage during winding and operation. Number three, winding quality. Definitely, that one is better rather than direct contact. Keeps turns neat, evenly spaced, and organized. Thermal management. Some formers are designed to improve heat dissipation, helping reduce eddy current losses. Better stability. Holds the winding firmly in place and prevents movement due to vibration or thermal expansion. Repeatability and consistency. Ensure identical coil shapes and dimensions across the multiple units. Also offer pins, something like those, or slots for easy connections. It's about time to have an example. Example number one is a straightforward example. An iron core has a relative permeability of 1500, a magnetic path length of 30 cm, cross-section area of 2 cm square. A coil has 100 turns. We need to calculate the coil inductance. If there is a current of 1 ampere flows through the coil, we need to determine the flux density B. We have assumptions here. Leakage flux is negligible and the core has no air gap. So what's given? So given here mu r, L, area, and N. So L equals N square over reluctance. So reluctance equals L over mu node mu r area. L equals 0.3 over 4 pi 10 to the power minus 7, 1500 to 10 to the power minus 4. That one is going to give us 795.8 10 to the power 3 ampere Weber. So the inductance will be N square over reluctance will be 12.56 millihenry. I said that one is a straightforward problem just to calculate the inductance. But if we have this inductance, we have now 1 ampere, what will be the flux density? We know that's Ni equals phi reluctance, so phi equals Ba, so in this case, B equals Ni over area multiplied by the reluctance, because we know that Ba is phi, so that one will be 100 turns multiplied by 1 ampere over 2, 10 to the power minus 4, multiplied by the reluctance value. That one is going to give us 0.63 Tesla. Let us elevate the level of the problem and take example number 2. Consider the magnetic circuit shown in figure A. That one. We covered this magnetic circuit in the previous video. A coil is wound on the central limb. The magnetic core is composed of 2 sections, E section and I section, each having a uniform depth of 1.6 centimeter. So we know the depth now. The 2 sections are in direct contact as shown in figure B. So in this case, we have E section and I section. They are connected together, forming a closed magnetic path with no air gap. The relative permeability of the core material is 450. So that one of the assumptions that we assume that the permeability here, relative permeability, is constant. We need to determine the inductance of this core. If the I section now is separated from the E section as shown in figure C, so we are going to add here air gap, something like 2 millimeter air gap. So we are going to insert something like a paper or a piece of plastic. So that one is if we have air gap by 2 millimeter. We need to calculate the inductance if the number of turns is 100, 150, and 200 turns, using calculation, using finite element analysis, and using measurements. Case number 1. No separation between E and I sections. So all the dimensions here are in the magnetic circuit, And the electric circuit equivalent to this magnetic circuit is shown here, and we covered that one in the previous video. So please refer to video number 3, how to calculate the equivalent reluctance. So as you can see here, R3, 4, 5, 6, 7, all of them are in series, in parallel with the other side, and then we are going to add them to 1, 2, and 8. So the equivalent reluctance in this case will be 733.71 10 to the power 3 ampere per Weber. The inductance in this case will be N square over reluctance or total reluctance. So for 100 turns, we have something like 13.63 millihenry. For 150 turns, we have 30.67 millihenry. And for 200 turns, we have 54.52 millihenry. Case 2. Separation between E and I sections by 2 mm air gap. So this is a magnetic circuit and all the dimensions are there. And then we have the equivalent electric circuit. So again, please refer to video number 3, how to calculate the reluctance of that one. So I'm going to add the link of the video in the comments. So those will be in series parallel to the left side. So that one will be in parallel with this one and then series to the middle limb. So the equivalent reluctance will be 7.159 10 to the power 6 ampere per Weber. What is the inductance in this case? So L equals N square over reluctance total. For 100 turns will be 1.4 millihenry. For 150 turns will be 3.2 millihenry. And for 200 turns, 5.6 millihenry. Quick observation here. So we notice that addition of the air gap is going to reduce the inductance massively. So I simulated this magnetic circuit using finite element software FEMM 4.2. So without the air gap, this is the flux distribution. So I added for you in the comments as well the link for this software or these videos, FEMM 4.2 software. So for 100 turns, we measured the inductance. We found that one 17.2 millihenry. And for 150 turns, we found that one 38.6 millihenry. And for 200 turns, we found that one is 68.6 millihenry. Definitely there is a difference between the calculated one and simulated one, and that one because the finite element software is going to consider all the effects. With air gap, we are going to repeat that one. So for 100 turns, we are going to find that the inductance drops to 2.1 millihenry, and for 150 turns, we are going to find the inductance is 4.8 millihenry, and for 200 turns, we are going to have 8.5 millihenry. So let's test this magnetic circuit practically. I'm going to measure the inductance when we have 3 different coils, 100, 150, and 200. We're going to move to another screen now just to test this one and measure the inductance in each case. Let's go. As we can see here, we have 3 coils, 100 turns, 150 turns, 200 turns. And these are the laminations, or this is lamination just to form this magnetic circuit. So that one is the I section and E section. So they are combined together to form the I section and the E section. And we are going to measure the inductance using this device. First, we are going to start with no air gap. And the first coil is the 100 turns. To add an air gap of 2 mm, we're going to use this piece of plastic here. So we're going to put it in the top of the central limb. And then we're going to put the I section like this way. So we are going to start by 100 turns again. Back to our slides, we are going to have some highlights from the comparative study between calculated finite element analysis and measured. And they can be summarized in this figure. So the top family of curves are for the inductance with no air gap and the bottom one with air gap. So number one, inductance increases as the number of turns increases. That one is a fact. With no air gap, there is a low reluctance and inductance rises with turns. With air gap, there is a high reluctance limits the flux to build up and there is a flatter slope. Calculated results are based on simplified formula L equals N square over reluctance and assumes uniform flux, no fringing and ideal geometry. This leads to underestimated inductance. For the finite element analysis, that one predicts higher inductance as it assumes ideal material and may not fully capture losses or imperfections. Regarding the measurement, counts for leakage, fringing, and material nonlinearity, and typically between the finite element analysis and calculations. But if you notice during the measurement time, the accuracy for the air gap is not 100%. So that one, it depends on how closely the I section connected to the E section. So that one is not 100% zero air gap, not 100% 2 millimeter air gap. The curves are not perfectly quadratic. Core material may start to approach magnetic saturation at higher number of turns, which reduces the rate of increasing the inductance. Let's take another example. Example number 3. In this example, we are going to design a specific value for a magnetic inductor. So design a magnetic inductor that achieves an inductance in the range of 5 millihenry. We are going to use M50 silicon steel core, where the typical BH curve for the M50 is shown in the figure. The core must have a rectangular geometry to satisfy the customer requirements. Maybe there is a limitation in the circuit board. The dimension constraints are maximum mean height is 5 cm, maximum mean width is 5 cm, maximum window height is 4 cm, maximum window width is 4 cm, and the maximum depth in any direction is 1 cm. So definitely the dimensions can be different rather than these values, but lower, not higher. The inductor must be designed such that the flux density remains below the knee of the BH curve of M50, which is lower than 1.4 Tesla. This is to avoid saturation and ensure linear opening. So what we need to obtain a practical inductor design. So we are going to identify the number of turns and the dimension. So design requirements. Determine the required number of turns. Determine the maximum current to ensure the maximum flux density remains safely below the knee of the BH curve. We need to verify this design and study the effect if we are going to inject in this core 1 millimeter air gap. What will be the consequences? Assumptions. Uniform flux distribution across the core cross-section. We can ignore the fringing. Core loss and winding resistance are not counted in the design. Let's start. So now it's given that inductance should be 5 millihenry. To ease the solution or to ease the design, we are going to start by the maximum allowable values, where the L, the mean length, is 5 cm plus 5 cm multiplied by 2 will be 20 cm. And the cross-section area will be 1 cm multiplied by 1 cm will be 1 cm square. If we choose the window will be 4 by 4 and the mean length is 5 by 5, that one is going to give you the area anywhere 1 cm square. From the BH curve, if we choose a point something like 1.3 Tesla, that one is going to give us H in the range of 575 ampere per meter. So the starting point of the design to choose B and H, so we should have a values lower than that one or equal to that one. So from B and H, we know that B equals mu node mu R H. So we can calculate mu R from that one. So mu R will be in the range of 1800. So we are going to use this value in our design. Then we can calculate the reluctance of the core. So the reluctance will be L over mu node mu R area, 0.2 over 4 pi 10 to the power minus 7 multiplied by mu R multiplied by the area 1 10 to the power minus 4. So that one will be 0.884 10 to the power 6 ampere 10 per Weber. Once we know the reluctance, we can calculate now the number of turns for this inductance, 5 millihenry. So 5 millihenry gives you 67 turns. That value, I can consider it low, but we are going to use it. So what will be the maximum allowable current? If we choose 1.3 Tesla, so in this case, we are going to calculate the current. You know that Ni equals phi multiplied by the reluctance. So Ni equals BA multiplied by the reluctance. So we can calculate I from this equation. So the maximum allowable current is 1.72 ampere, which is low value. So we cannot go beyond this value, else the core will be saturated. Let's verify this design using FEMM 4.2 software. So we build this magnetic circuit in the FEMM 4.2. We have this flux distribution and we have this contour to calculate the flux. So the flux across this contour will be 1.33 Tesla here, 1.33 Tesla there. So the current is 1.72 ampere and the flux is 1.33 Tesla. What will happen if we increase the current? Definitely, as you can see here, the color becomes more darker. So this means that we are in the saturation mode. So the flux reaches something like 1.62. For 5 ampere, 1.62 Tesla. What that means, we are in this region in the BH curve. And that one is not accepted in our design. So what we should do to have more current without saturation? Let's try another design to inject 1 millimeter air gap in our. So in this case, we are going to calculate the reluctance of the gap, G over mu node area. So the reluctance of the air gap now is 7.96 10 to the power 6 ampere turn per Weber. And the reluctance of the core we calculated before. So the total reluctance would be something like 8.84 10 to the power 6 ampere turn per Weber. So what will be now the number of turns? For the inductance 5 millihenry, the number of turns could be 210 turns. Right? So the current for the maximum accepted flux density, which is 1.3 Tesla, so that one will be BA reluctance total over N. In this case, we can reach up to 5.47 ampere. Please bear in mind that I ignored the leakage and fringing in this design, and I take the mean length back. Based on the design values, I tried to verify the design using FEMM 4.2 software and a lot of iterations until I reach that the number of turns could be 172 turns and the coil current is 4.5 ampere. Let's look here. So we have that one will be the core and that one will be the flux distribution. So across this contour, so we have here 1.33 Tesla and in the air gap 0.86 Tesla. So the inductance is 5 millihenry. The flux density in the main limb will be 1.33 and in the air gap will be 0.86. This will be the final design. So we have 6 centimeter in each side and we have 1 centimeter depth. The window will be 4 centimeter by 4 centimeter and the number of turns will be 172 turns and the current 4.5 ampere. Maximum allowable current is 4.5 ampere. So someone is going to ask, if I put something like 2 ampere, is the inductance is going to change? Please don't forget the inductance equals N square over reluctance. So that one is not going to change, but the core will not be saturated. But if you put something like 6 ampere, the inductance will be in the range of 5 millihenry again, but the core will be saturated. What will I watch in video number 5? In video number 5, we are going to cover losses in magnetic circuits and magnetic coupling. See you in the next video.